Many aspiring statisticians and data scientists encounter a crucial distinction: the sample mean is not the expected value. While these terms are often used interchangeably when simplifying ideas, their precise definitions and implications differ fundamentally. Understanding this is key to robust inferential statistics. This video will clarify why, despite apparent similarity, these two concepts represent distinct ideas, though closely related. Let's begin by defining the expected value, often E, X, or mu. This theoretical concept from probability theory represents the long-run average of a random variable if an experiment were repeated infinitely. It's the weighted average of all possible values, with weights being their probabilities. Think of it as the true population mean, a fixed, often unknown parameter inherent to the probability distribution. For a discrete random variable x, the expected value is calculated as the sum of each possible value multiplied by its probability, e x equals sum I xip, x equals xi. For a continuous random variable, it involves an integral, e x equals integral minus infinity to the power of infinity xf, x dx, where $f, x, $, is the probability density function. This value is a property of the probability distribution, not specific observations. Now, let's turn to the sample mean, typically denoted as bar x. The sample mean is an empirical concept, a statistic calculated from a finite set of observations, a sample, drawn from a larger population. We collect a limited number of data points, sum them, and divide by the count. It's a single numerical value derived directly from your collected data. The formula for the sample mean is straightforward. For n observations x1 dots xn, the sample mean is bar x equals 1 over n sum I equals 1 to the power of n xi. This value is a descriptive statistic summarizing the central tendency of your specific sample. Unlike the expected value, the sample mean is not a fixed theoretical parameter. It changes from sample to sample. The core reason a sample mean typically isn't the expected value is sampling variability. When you take a sample, you observe only a subset of the data-generating process. Due to chance, your specific sample is unlikely to perfectly reflect the underlying population distribution, so its mean will almost certainly deviate from the true expected value. Each new sample yields a different sample mean. Here's the crucial link. While it isn't the expected value, the is, in fact, equal to the population expected value. This property makes the sample mean an unbiased estimator. Mathematically, E bar x equals E x equals mu. Taking infinite samples and averaging their means, that average would converge to the true population expected value. Consider flipping a fair coin. The expected value for heads in one flip is 0.5. If you flip it 10 times, your sample mean might be 0.4, 0.6, or 0.3. This single sample mean is unlikely to be exactly 0.5. However, repeat this 10-flip experiment many times, say 1,000, and the average of those sample means would indeed be very close to 0.5. This brings us to a fundamental theorem, the law of large numbers. Simply put, as the sample size n increases, the sample mean bar x converges in probability to the expected value E, x. This means a larger sample provides more confidence that your sample mean approximates the true population expected value. The law of large numbers guarantees that with a sufficiently large sample, random sampling variability diminishes significantly. Your sample mean will get arbitrarily close to the true population mean. While a small sample mean might be far off, a very large sample mean is an excellent estimate for the expected value. It's about consistency, not exact equality for any single finite sample. Understanding this distinction prevents common statistical pitfalls. For instance, in a small A/B test, an observed sample mean difference cannot simply be equated to a true population effect. Small sample means are subject to considerable random fluctuation. Overinterpreting them as definitive parameters often leads to incorrect conclusions. In practical applications, especially with large datasets, the sample mean is often used of the expected value. When n is large, it provides a reliable point estimate. However, remember it is still an estimate, subject to confidence intervals and hypothesis testing, accounting for inherent uncertainty. We never truly the expected value from a sample. In summary, the expected value is a theoretical, fixed parameter of a probability distribution, representing the true population mean. The sample mean is an empirical statistic, calculated from a finite sample, varying from sample to sample. A specific sample mean is unlikely to equal the expected value, but the expected value of the sample mean is the true expected value, making it an unbiased estimator converging with increasing sample size. Grasping the difference between the sample mean and the expected value is fundamental for anyone working with data. It underpins concepts like estimation, hypothesis testing, and statistical inference. Always remember that while your sample mean provides valuable insight, it's an observed value from a finite snapshot. The expected value describes the underlying, often unobservable, reality of the entire population.